Welcome everybody. It is 6 p.m. on June 23rd, 2020, and this is the first year of the drinking water trend data analysis in Greene County. I'm Victoria Solomon. I'm the Community Resource Development Educator with Greene County Extension. I'm happy to introduce Kevin Masarik, the Groundwater Education Specialist with Extension in the College of Natural Resources at UW-Stevens Point. He will be sharing information about this year, the first year of the Greene County groundwater trend quality work. So Kevin, with that, I'm going to hand it over to you.
Thanks, Victoria. And I'm gonna share my video just for a second and just say thank you to everyone that participated. This project is a collaboration between Greene County, our center here at UW-Stevens Point, which is also affiliated with University of Wisconsin-Madison Division of Extension. So this really is a partnership that is not possible if it weren't for all of you being willing to participate in this program. So I see a lot of familiar names showing up on the screen because I've been the one that's been communicating with a lot of you. We would have liked to have done this in person. Obviously, the circumstances we find ourselves in, that's just not possible this year, but potentially in future years, maybe we'll have the opportunity to do an in-person meeting to eventually share results. But in the meantime, I hope that the information that was provided with your results, hoping that you received them, was useful. And then we're gonna try to fill in some of the blanks in terms of any questions you have, but also what's the big picture? What's the intent of the project, and then where do we go from here after year one? So years 2 through 5, what do those look like, and what do we expect of participants moving forward? So with that, today in the brief time that we have together, what I'd like to cover is just a little bit about the basics of groundwater in Greene County, which I think will help explain some of the impetus for the project and why you may have been selected to participate. We'll provide an overview of the project goals and process, talk a little bit about the individual tests that we performed and what that means in terms of your water quality, whether it's for drinking or maybe aesthetic reasons. We'll try to highlight why we do certain tests. Throughout the presentation, we'll talk about what we've learned so far, and then also looking forward, again, we'll highlight what comes next. And then we'll end with a little bit of Q&A if there's any unresolved issues that people might have. So just highlighting here, the basics of groundwater are that our groundwater, your well water, doesn't come from Canada, doesn't come from Lake Superior. Your well water is just basically rain or snow melt, some of which infiltrates into the ground, eventually reaches a point where all the empty space in the soil or all the cracks in the rock are filled with water. That's our groundwater. That's also the area or the reason why you have the opportunity to install a well and bring water into your homes. We're pretty fortunate here in Wisconsin that groundwater exists basically everywhere below our feet. So in the vast majority of cases, you can stick a well pretty much anywhere in the state of Wisconsin and get ample water, and usually that water is of pretty good water quality as well. The other thing about this diagram to point out is that groundwater is always moving very slowly through the empty spaces in the soil or the cracks in the rock to a nearby discharge feature, which is typically going to be represented or expressed on the land surface as a lake, river, stream, or wetland. So that's basically the most simple explanation of groundwater is it's rain or snow melt that infiltrates into the ground and moves slowly through the pore spaces in the rock or the soil to nearby lakes, rivers, streams, and wetlands. The properties of those rocks, the properties of the soil are really important for determining things like how quickly groundwater moves, but also how easily groundwater becomes contaminated. So if we think of water moving through large cracks or fractures in rock, that water is obviously going to be able to move much quicker. There's going to be less filtering ability by the material. make it maybe more easy to become contaminated in certain situations than water moving through tiny spaces in between sand or soil particles. So groundwater scientists, and we're going to talk about that a lot today, we're going to talk a lot about geology and soils because that's really what stores and holds our groundwater and our well water resources. If we want to get a sense for how groundwater moves, we look at watersheds and watershed boundaries. This gives us some idea of where the water might originate for our wells or for lakes, rivers, streams, and wetlands. So here we see a map of Greene County, and the dashed green lines represent kind of small watersheds. And then we have a fairly large or major groundwater divide flowing north-south, represented by this thicker gray line. That's just highlighting water that flows to the Sugar River watershed versus water that flows over into the Pecatonica River watershed. And if we want to get a sense for how far that groundwater moves, most water is just moving to the nearest discharge location. So the point being that your well water, your groundwater here in Greene County isn't coming from far away. Typically, in most situations, I think with typical private wells, you could look at the water originating within a quarter or maybe a mile of the well itself. And if we know a little bit about the direction that groundwater flows in, you might have a little bit better picture for where that water is coming from. But the message being that basically what happens locally on the landscape, what types of material occur locally in the groundwater, really are going to help determine individual well water quality. So that gets to the next slide here, which is just talking about water basics and water chemistry, and that we call water the universal solvent because it naturally has the ability to dissolve stuff into it. We call those things that water dissolves impurities, and those impurities depend on the rocks and minerals that water flows through. It depends on the types of land use, even the types of plumbing and packaging that water is stored or transported in might impart different impurities. When impurities reach a level of concern, and not all impurities will cause health effects, but for those impurities that do have health effects associated with them, they could eventually become some sort of health-related contaminant. And that's why it's important that we know at what level some of those contaminants would be considered a health risk or a health advisory or health concern. And that's some of the things we're going to do today is talk about some of those tests that might have health effects and help you better understand what those safe levels are. And if people are dealing with either aesthetic problems or health-related issues in their water, we can talk a little bit about what people are able to do to treat that water or make it safer or better quality for your intended purposes. So highlighting again the geology, the term you may have heard before, this term aquifer, is just the fancy name we give to our groundwater storage units. And I think it's just important to point out that Wisconsin's geology is very diverse. We have this layered cake geology with what we call crystalline bedrock occurring everywhere in the state of Wisconsin. Some places that occurs very deep, like in Greene County. The crystalline bedrock may be very near to the surface in northern Wisconsin. Here in Greene County, there's also going to be alternating layers of sandstone and dolomite. And then those sandstone and dolomite layers are oftentimes covered by sand and gravel or other deposits that were left behind by the glaciers. So knowing a little bit about the geology where you live can help us understand what water quality might be like, or maybe how susceptible groundwater in an area is going to be to certain land use activities. And if we zero in or narrow in a little bit more on Greene County geology specifically, what we'd see is that the dominant bedrock geology is going to consist in some places, shown in the brown or light brown, those would be areas where we have what we call dolomite rock. Some people might refer to it as limestone. It's very similar to limestone. It just has, instead of calcium, it has a higher concentration of magnesium as well. But that type of rock tends to be highly cracked or fractured, which we've already discussed how cracks and fractures can maybe make groundwater a little bit more susceptible. There's other areas that you see outlined in pink where the uppermost bedrock layer might be what we call sandstone. And sandstone is a little bit better filter for things like bacteria that would make it a little bit more difficult for those things to find their way into somebody's well. So the point being here is that Greene County bedrock geology is very diverse. And then if we look at basically how deep is it to groundwater, not to groundwater, but how deep is it to bedrock, that's what this map here is illustrating, is the depth to bedrock. So basically, how deep are the soils or the other unconsolidated materials that have been left behind by the glaciers, or maybe erosion of river and stream valleys. And in a lot of Greene County, it might be no surprise to a lot of you that the soil layer is oftentimes very thin when you get on top of hilltops in parts of kind of western and southern Greene County. If you look closer at the area near the Sugar River, what you see is much deeper unconsolidated deposits that in some cases might be 100 feet or more of sand and gravel or other materials that also hold and store groundwater. So this is also very critical for determining things like groundwater quality or contamination susceptibility. The other thing we'll notice is that the soils themselves are quite diverse. This map just shows the permeability of different soils, with the areas in orange being highly permeable, areas where we might have maybe sand, and then the areas in green or darker green where we might have silt or more silt loam type of soils that maybe offer a little bit more protection for that water that's soaking into the ground as it becomes groundwater. And then complicating things even more is that land use is quite complicated or quite diverse in Greene County as well. So here we see a land use map, a very general land use map for Greene County. The areas in red would signify kind of more urban areas near villages or cities. And then the green areas would be forests or shrublands, and then the orange areas might be agricultural areas. And if we were to look even at the agricultural areas, what we'd see is that even that agricultural landscape is quite diverse as well. So all of these things are really factors that might help explain why certain contaminants like nitrate or chloride might be found in somebody's well, or things like hardness or alkalinity, which come from geology, might occur at higher concentrations in some people's wells versus others. So the last thing I want to highlight in terms of groundwater basics is just talking about the role of well construction in also determining where a person gets their water from, as well as how well casing and well depth help determine water quality. So in this diagram, which might represent an area in Greene County where you have dolomite or carbonate rock where the soil layer is very thin, you might have a well that's fairly deep, but these black lines might represent the depth of that casing. So the casing is that metal pipe that sticks out of the ground, also extends a certain distance below the ground. And if that casing only extends to the top of the water table, it means that this whole section of the well, basically from the top of the water table to the bottom of the well, is open to the aquifer. That makes it much more susceptible to things that infiltrate or soak into the ground near the well. It's going to be much more susceptible to certain land use activities in close proximity to that well. If we were to deepen that casing, so in this case, the well depth is the same, but we extend that casing deeper into the aquifer, you can see that we're suddenly pulling water flowing to that well is coming from much deeper in the aquifer, likely coming from further away, and it's going to be a little bit more protected from what goes on the land surface simply by the depth of the casing or extending the casing into the aquifer. So all these things, geology, soils, well construction, will be important factors for why water quality, somebody's well water quality, behaves or contains certain impurities. And if we start transitioning into the study, I'm sure a lot of people are asking, why was I selected? And I just want to kind of roughly go over our recruitment strategy, which is we wanted wells where we could get good information on the well construction and the well history. So wells drilled after 1988, it makes it really easy for us to locate that information. There's a unique well number, which is unique to somebody's well, that we can match up to that well's well depth, the casing depth, depth to water, and the geology that well was installed into. That's extremely useful information for us as we start piecing together bits and pieces of this project. We attempted to find one well per section that, again, was drilled after 1988 with the unique well number and good well construction information that could be matched to an individual parcel with a high degree of confidence. So in some cases, those records might not be good enough to be able to say with a lot of confidence that the well is located in a certain parcel. That makes it really hard to contact the individual who might own that well. So the wells that we selected were of that criteria, and we attempted to find one well per section to communicate with or to recruit for the purposes of this project. All things being equal, a lot of times there's more than one well per section. All things being equal, we usually gave preference to people that participated in previous extension well testing efforts, because we have some previous testing data that might also be come in handy at some point in time. Where and how many wells did we try to recruit, and how many were we successful in sampling? This just gives you some idea of that initial recruitment process. That's that map on the left showing 778 landowners who we reached out to and asked them if they wanted to participate in this study. Of those that we contacted, 388 landowners indicated that they were willing and interested, and ultimately 342 people actually submitted samples for this year's project. And the map on the right shows kind of the distribution of where those samples came from. And what I hope you'll see is that it's fairly distributed across Greene County. And again, that's going to give us a lot of ability to feel really good that this study or this project is truly representative of the diverse land use, geology, and soils of the area. And really our goal, the goal that we set out to do, and the reason the county was interested in this study in the first place, is we're looking to investigate how and whether water quality or well water quality changes over time. So the analogy I always use is that we're almost trying to establish the Dow Jones Index for Greene County well water quality. We want to be able to say in 5 years, is well water quality getting better, worse, or staying the same? And if it's changing, what can we learn about where and why those changes are taking place? If groundwater or well water quality is improving, what can we learn that might be replicated in areas where it's getting worse or not changing for the better? Those are all goals that we hope to accomplish. This project is going to works best when the wells are representative of the diverse area that we're working in, which we feel that it currently does. But our hope is that the same wells are sampled every year, and that's really why we're hoping that all of you are interested in participating for years 2 through 5. A little bit about year 1 and in the process that all of you participated in. The recruitment happened prior to January, but in January we mailed everybody a sample kit. The participants collected samples in February, some even into March, and then mailed them back to the lab. March and April, those samples were analyzed, and then about a month ago or a month and a half ago, we would have mailed results out to each individual. And right now we're at the education session phase where we're trying to give you a preview of what we've learned before culminating our annual report that we'll submit to the county board. So the information you're seeing here is the first time any of this information is presented. We wanted to give project participants the first, the first look at what information we've been able to learn from the project. What tests were performed? Just reiterating what's on your results sheet. The tests that we performed would have been nitrate and chloride, which are useful for understanding land use impacts. We would have also tested for total hardness, alkalinity, and pH, which provides some ability to understand how the rocks and soils impact groundwater. And then conductivity is kind of an overall water quality test that combines both land use impacts as well as how the rocks and soils might be impacting water quality. And looking at changes over time, really what we're hoping to understand is maybe how land use might be changing water quality, but also how does water quality fluctuate from year to year based on weather variability or precipitation patterns. Those are also things that we might be able to tease out of the information during the course of this project. So getting into the actual individual tests that were performed and helping you understand a little bit about how to interpret those results, the first one I want to start off with is what we call total hardness. Hardness is simply a measure of calcium and magnesium in your well water. Calcium and magnesium are naturally occurring. We find them in dolomite rocks, which are prevalent in much of southern and southwestern as well as eastern Wisconsin, not so much in northern Wisconsin, which is why the water in northern Wisconsin typically tends to be softer or not as hard. But southern Wisconsin, because of the dolomite rock aquifers, it's fairly common to have what we call hard water. And hard water would be anything with concentrations of hardness greater than 200 milligrams per liter of hardness. And the problems associated with hard water would typically be scaling, soap scum buildup. People with hard water tend to use more detergent or soap. And hard water, if left unchecked, can decrease water heater efficiency over time. Because of the ability of that water to form scale, those would be all issues associated with hard water. Those with hard water, again, anything over 200 milligrams per liter would kind of be considered that hard water. Water softeners are kind of a tried and true technology for minimizing the negative impacts associated with the calcium and magnesium in water. Water softeners remove calcium and magnesium, and they exchange it for elements like sodium or maybe potassium, depending on what type of salt you use, that typically don't cause the same issues that calcium and magnesium would. Considerations for softening are that it does increase the sodium content of the water. So that added sodium could be problematic for people that are on low sodium diets. And it also increases or it will discharge chloride to groundwater, which the amount discharged isn't, it's not that big of an issue, but that can be a concern in some areas, especially where there's maybe a higher density of people on individual private wells and septic systems. So in order to minimize the amount of either sodium we're exposed to or chloride we're discharging to groundwater, some suggestions that often are provided to people are that, you can oftentimes bypass your primary drinking water faucet if you don't want to be exposed to those elevated levels of sodium. The majority of people probably prefer the taste of calcium and magnesium in their water for drinking. They just don't like all the other problems that it causes for washing dishes, bathing, or other scaling issues on fixtures and faucets. The other thing we'd advise is, if possible, you don't need to soften water for outdoor faucets. That's one way to save on salt and reduce the amount that ends up in our groundwater. And then look at, regenerating your water softener based on volume rather than a set period of time. Depending on the model water softener you have, that might not be an option. But if you're ever looking to replace your water softener, looking to purchase one that regenerates based on volume would be one way to save on the amount of salt that maybe unnecessarily is used. And again, if you're using or concerned about sodium levels and you do want to soften your drinking water, potassium chloride softener salt might be a little bit healthier alternative for people if they're going to be drinking softened water. Some of the other tests that we performed would have been alkalinity. And alkalinity is just the ability to neutralize acid. And the reason we do this test is it helps us determine how corrosive water is likely to be. In areas where water might have low alkalinity, that could increase the corrosivity or the ability of that water to corrode household plumbing. Typically, alkalinity levels greater than 200 are going to have the opposite impact, which is a greater tendency of that water to form scale and contribute to scale formation with the hardness concentration. And then pH is something else that we tested. Most people are familiar with pH in that it's a measure of water acidity. We know that things that are acidic, that would be concentrations of pH less than 7, would tend to be more corrosive than pH is greater than 7. Typical pH in Wisconsin is anywhere between about 6 and 9, and that's a fairly wide range across the state, but it's likely going to be much narrower in Greene County. So this is kind of what one way in which we display the information is through generic maps. So we never want to basically give away or display information from this project at a level that would enable someone to see a site-specific or a individual well water quality at somebody's site-specific parcel. But these very generic maps will give you some idea of how water quality varies across Greene County. So these maps here just show the concentrations of alkalinity, total hardness, and pH that were measured in the 342 samples that were submitted. It also shows the average concentrations that were measured, and then hopefully gives you some indication of how variable those concentrations were across the county. And one thing that you'll see is that areas where alkalinity was low are also areas where the hardness was low, and areas where the pH might have also been a little bit lower. And what we know, what we've talked about already, is how the rocks and the soils impact groundwater quality. And really that's one thing that we're seeing here, is that both the alkalinity, the hardness, and the pH are being impacted or will be slightly different depending on the types of geology that your well encounters. If it's a sand and gravel well, or if it's installed in an area with sandstone, it's much more likely to have lower values of things like alkalinity and hardness. So that's what this slide here is illustrating. Is just giving you some preview of what we're hoping to accomplish in the future years, is that we'll take a much deeper look at that relationship between these wells that are tested and the types of geologic material that they're drilled into, or things like the depth of the well or the casing depth in determining your water quality. Another test that we performed that we talked about briefly was chloride. We mentioned that chloride and nitrate are tests that we do because they're associated with land use impacts. Typical natural levels of chloride in Wisconsin's groundwater, we would expect to be less than 10 milligrams per liter. When concentrations get above 10 or greater than 10, we associate that with some sort of human impact. And then if concentrations get greater than 250 milligrams per liter, there's no health effects or direct health effects from that, but that amount of chloride in water might give it a kind of a salty taste, and it might also cause kind of a speeding up of corrosion on household plumbing. Fortunately, nobody in Greene County tested above 250 milligrams per liter through this testing program. But that's one way in which you can kind of help interpret your chloride numbers, is looking at if it's less than 10, we would assume that's kind of natural levels. If it's greater than 10, there's some impacts. And what would those impacts be? Chloride could come from fertilizers, mainly potash. A lot of times is potassium chloride. The plants need the potassium, but that chloride can be released and end up in groundwater. Septic systems, the chloride that is generated in human waste or might be generated during the softening process is sent to a septic system drain field where it could eventually find its way into groundwater. And then also road salt activities in winter are great for de-icing roads, but that snow ends up in the culverts and the ditches. And when that snow melts, it often contains a high concentration of chloride, which can be ended up carried into the groundwater and sometimes shows up in people's wells. If we look at the chloride results from the 342 participants, this map here shows kind of concentrations of chloride from the lighter concentrations to the darker being higher concentrations. And one thing that's, I think, pretty obvious from this map, at least to me and hopefully in the future to the participants, is that the closer you are to kind of villages or major roadways, oftentimes that's where we see the highest concentrations of chloride, which again is no surprise if we think that, you know, septic system drain fields or road salting activities in urban areas or on major roadways might be impacting groundwater quality. It wouldn't be a surprise to see those high concentrations near those more densely developed or urbanized areas. The summary shows that there is a very small number of wells, 2%, testing greater than 100 milligrams per liter. So that's great news. Also great news is that 41% of all the wells tested less than 10 milligrams per liter. So that would again be the natural or background levels that we would expect to find in groundwater. The average concentration was 19.1, so there definitely are areas where we see impacts from land use. And then the maximum concentration was 175 milligrams per liter. The last test that I want to talk about that we performed would be the nitrate nitrogen test. This is the only test with kind of direct health implications to people if they're using it for drinking water. Less than 2 milligrams per liter, we would typically associate with kind of natural or background levels of nitrate in Wisconsin's groundwater. Levels above 2, we tend to associate with water that's been impacted by human activity. If it's above 2 and below 10, we still consider that water to be, you know, perfectly suitable as a drinking water source for most populations. When it gets above 10, however, that's where we would consider that water to be unsuitable or unsafe, unsafe for infants, pregnant women, and we would encourage everyone to avoid long-term consumption of nitrate above 10. Infants and women who are pregnant really should never be drinking water with levels above 10 milligrams per liter. And everyone else, we'd again try to encourage them to avoid long-term consumption of water with nitrate above 10. Some of the health effects associated with nitrate, and this information comes from the Wisconsin Department of Health Services. Methemoglobinemia or blue baby disease is something that can impact infants less than 6 months of age. Women who are or may become pregnant, the concern is possible links to birth defects, as well as miscarriages, not only in humans, but also in livestock. And then when it comes to older populations or everyone, the concern of long-term exposure to high nitrate levels would be an increased risk of thyroid disease or maybe increased risk of certain types of cancers. The sources of nitrate to groundwater would be nitrogen agricultural fertilizers, maybe animal waste or other biosolids that are spread on agricultural fields or stored or stacked in certain areas. Septic system drain fields would be expected to release a certain amount of nitrate to groundwater as well. And then lawn fertilizers, it would be great if all that nitrogen was taken up by the grass, but some amount of that nitrogen is also likely to escape below lawns, just as it would an agricultural field. So it's really important that we try to minimize or manage those nitrogen sources as best as possible to ensure that they don't end up contaminating our groundwater. What we see from the nitrate results are illustrated here in the map, the general map of water quality results from the 342 tests. The summary shows that 15% of the wells tested greater than that 10 milligram per liter drinking water standard. The statewide average for wells that exceed the drinking water standard is about 10%. So Greene County is slightly higher than the statewide average. And what you'll see is that the location of those wells above 10 is not necessarily random. There are certain patterns which would make it more likely to exceed that 10 milligram per liter in some parts of the county versus others. Also, what you'll see is that about 28% of wells tested less than 2. So those are wells that would be considered to be at background or kind of natural levels, meaning that 82% of wells, or I should say 72% of the wells, are showing some evidence of impacts from land use activities that we talked about in the previous slide. The average nitrate concentration was about 5.3, and the maximum concentration measured was 26.8. If you are dealing with nitrate levels, this is something that if you're using your well water for drinking, we would encourage people to try and reduce those levels if your concentration was above 10. The ideal solution is to try and eliminate the contamination source or reduce nitrogen input somehow. That's not always possible if you don't control the land which recharges your well water. Even if it is possible, it might take years or decades to notice measurable improvement. So unfortunately, in the short term, oftentimes people are looking at other options such as would changing the well depth or relocating the well help improve the situation. Other people might choose to look at purchasing or using bottled water until they can find a long-term solution. Other people might choose to rely on some sort of water treatment device to reduce the concentration of nitrate in their drinking water. Because it's only a drinking water concern, we're not concerned about high levels of nitrate for things like washing dishes or bathing with it. Because it's a concern for drinking water only, a lot of times you can get away with a water treatment device that just treats the water at your primary drinking water faucet. So treating a small quantity of water for that particular use. And water treatment specific or capable of reducing nitrate would be things like reverse osmosis, distillation, or anion exchange. A lot of people have the question, does my water softener help reduce nitrate? And the answer would unfortunately be no. Same thing is true with maybe a carbon filter or a filter that you have installed on your refrigerator. Most of those filters are not going to be capable of significantly reducing nitrate from well water. They have capability to remove or improve kind of taste, color, odor issues. Unfortunately, some of those devices will not reduce nitrate. If your concern is nitrate, you really want to invest in a reverse osmosis, distillation, or anion exchange system. And we mentioned that nitrate and chloride are useful for understanding land use impacts on groundwater. So here is just a slide illustrating that fact, that when we look at areas where we have elevated nitrate, a lot of times they occur in areas where we have maybe a higher density of agricultural activity. In the future, we might even drill down deeper with our data set to investigate, are there certain crops that would make it more likely to find higher concentrations of nitrate in groundwater? The same thing's true with chloride, where we'll be looking at what's the relationship of maybe road networks or septic systems on chloride. How does fertilizer activity on agricultural fields impact chloride levels in the well water of people in Greene County? So those are all things that we hope to investigate in more detail in years 2 through 5, but I wanted to mention that we do know quite a bit about why certain areas have higher levels. It's just we'll be able to develop more or better predictive models that will help us predict well water quality for all the people that didn't necessarily participate in this project or this study. Lastly is conductivity. Conductivity, there's no health effects associated with this either, but it's kind of an overall water quality test in that it's measuring the total ions in water. Some of those might be hardness. A lot of times hardness is primarily responsible for the conductivity. So if we multiply the hardness value by 2, that should roughly equal somebody's conductivity value. If the conductivity is much greater, then it's probably an indication that there's elevated high levels of maybe chloride or maybe nitrate in that sample that are throwing the ratio between hardness and conductivity off a little. So conductivity is a fairly inexpensive test, but it has a lot of usefulness in helping to detect changes in well water quality over time, which is why it's included in this study. And it's one of those things that will help us investigate the relationship of water quality to maybe climate or weather variability as well. So where do we go from here? I just briefly covered some of the tests, why we did them, what they mean, and what we've learned. Year 2 is really where we're hoping to investigate this question of how is water quality changing over time. We're hoping to send test kits out sometime later this year in November. Some of that is going to depend on how things with COVID-19 shake out and whether the lab and us as professionals are able to function kind of in a way that allows us to carry out the study that doesn't put people at risk. So can we, ship bottles to you, and can we have you get them back to us in a safe and responsible manner? That might be something that dictates the timeline a little bit. But our goal is to try and mail test kits out sometime in November. And then when we're able to get the data back from years 2 through 5, we're going to begin to work investigating the relationships between land use, soils, geology, and well depth in a little bit more detail through the use of statistical models that will help us better predict water quality risks of those that are not part of this project. We also want to try to integrate temporal component to our data analysis for understanding changes over time. So looking to see, are there trends in individual wells? Are there parts of the county where a higher percentage of wells are getting worse? Or are they mostly staying the same? Those are all things that we hope to answer moving forward. And then lastly, we are working on a website to better communicate the project results. So some of the maps that you saw in this presentation are going to be interactive in the sense that people will have the ability, you will have the ability to not necessarily zoom in any closer, but interact with the data in a little bit more detailed way, which is going to be particularly relevant as we integrate those temporal components to this project. Being able to see the historical concentration of things like nitrate will help give people a better sense of how variable nitrate is from year to year, and whether it's increasing or decreasing in a repeatable way that would indicate some sort of trend. So I'm going to end or close with that, and I believe we have a little bit of time for question and answer. It's about 1:45. We understand if people aren't able to stick around, it's a beautiful night out from what I hear down in Greene County. But if people do have some questions, I believe that you can either enter them into the chat box or Victoria or myself will facilitate unmuting people's mics if necessary. If there's any questions about the project or that people have about their individual results. So I'll turn it over to you, Victoria, if you have any last comments or you want to facilitate the question and answer. But while Victoria's transitioning here, I just want to thank Greene County. The Greene County Board is really the reason this project moved forward. They are helping to sponsor the project. I also want to thank the Greene County Extension Office, as well as the Greene County Health Department and the Greene County Land Use and Zoning Department for their assistance with this project. If there's any questions, I think we'll take them. We'll take a few now. If people aren't comfortable asking questions here, or maybe can't get the technology to work right, you'll see my contact info is listed here, my phone number, as well as the email, my email address that people can use to contact me if they feel more comfortable asking questions through those mechanisms as well. And we do have one question here from Jim and Denise. If the sample kits are going to be mailed out in November, when would they be due back? And that's a good question. I think we would generally like to give people about a month. So if we mailed them back or mailed them out to people on November 1st, our hope would be that we could get them back in the lab within that month so that we can facilitate the analysis and do the analysis kind of all at once. We understand that people might not have access to the well during certain months of the year, which is why I think we want to do it earlier than we did this past year, just due to the fact that some people might go on vacation or may winter in Arizona or Florida. That was a challenge for some folks in that they weren't able to sample until they got back. By sampling a little bit earlier, I'm hoping that we might be able to avoid some of that. If anybody does have any issue with that timeline, please know that we will be flexible and work with you to make sure that you're still able to participate, even if that timeline doesn't necessarily work for you as an individual. We're hoping it will work for most people.
Hi, Kevin. So this is Victoria. I just want to share, if you could maybe clarify a little bit about the slide on chloride. I believe the slide on chloride indicated average and maximum concentrations of nitrate and nitrogen rather than chloride. So can you maybe clarify that a little bit, please?
Thank you. And I did see that Joe pointed that out as well to me during the presentation. In that here you'll see there's an obvious typo. This should read average chloride concentration of 19.1 and maximum chloride concentration of 175. So the numbers are right. The description is wrong. So thank you for all of you that caught that mistake.
Wonderful. Are there any other questions? You can unmute and ask, or you can type in the chat box. Okay. Well, thank you for joining everyone tonight. Thank you, Kevin, for sharing the information. I'm going to end the recording now. We will stick around if there are any questions or discussion that people would like to have. But again, thank you for joining.